So, metallic bonding. Metallic bonding is actually fairly straightforward because if it's a metal-to-metal bond, then it can be either the same metal or it can be different metals. If it's different metals, it just means that you have to represent two different size circles, basically. So metals, the specification says, metals consist of giant structures of atoms arranged in a regular pattern. Now, all that it means by giant structures is infinitely repeating. So if I say, okay, that's a gold atom here, that's a gold atom, then that's next to another gold atom, next to another gold atom, and it goes on and on and on and on, and that's it. Now you can see that I've just done a straightforward pattern here of one circle next to each other. It doesn't really matter in terms of the sort of packing that you get in the diagram. So let's have a look. Boop, 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 boom. The electrons in the outer shell of metal atoms are delocalized and so are free to move through the whole structure. So really you get the difference between covalent bonding and metallic bonding as polar opposites. In covalent bonding, let's say that's water, where are the electrons that bond the atoms together? They're here and there, and you know where they are. In metals, on the other hand, you've got metal atoms next to each other, and the outer shell electrons are shared around. So the outer shell electrons can flit between the atoms as they wish. And because the outer shell electrons are shared, that leaves the rest of the metal atoms as cations. So let's do a specific example. Let's say we've got lithium. Lithium has a electronic configuration of 2,1 in its pure metal form, which is of course very reactive. What happens is that one outer electron gets shared between all of the metal atoms, and if the metal atoms now have lost one of the electrons, they then become a cationic, basically. Now, what holds these positive charges together is the electrons themselves flitting in between the cations. So there's always a situation where you've got two positive charges and you've got one electron in the middle between them. And since they are on average equally distributed, the metal atoms do not repel each other. Metal cations, I should say. It says the sharing of delocalized electrons gives rise to strong metallic bonds. Now, the first thing we should explain is delocalized means they have no specific place. So I've just said, where are the atoms in the bonds between hydrogen and oxygen? They are the sticks. You know where they are. Here, they can go from one end of the structure to another end with no penalty at all. And of course, on average, that evens out. For group 1 metals, that's actually a fairly weak bond. And you've got sodium melting at below 100 degrees, for example. And they become more easily meltable as you go down the group. But if you've got proper metals, such as the transition metals, then the melting point increases, and that is partially a function of the sharing of the number of electrons in the outer shell. So copper, for example, shares 2 of its electrons, and that makes for a stronger attraction between the cations. So it's now got twice as many electrons as it has cations. Okay, that'll do. Okay, you see where I'm going with this. There's in fact a brick and mortar analogy, which means that if the cations are the bricks, the electrons are the mortar that hold the bricks together, and the more electrons you have flitting around, the more strongly they are held. Okay. That also means that what happens if you bend a metal? So if you go from a straight metal where you've got your metal atoms in a row, and then you bend it. And what happens is that the electrons act almost like a lubricant, and they allow the round metal atoms to flow over one another. Of course, we all know that metal fatigue is a thing, so if you bend them repeatedly, what you also do is you push those metal atoms apart, and it becomes thinner and eventually snaps. Okay.
Please like and subscribe, and let me know of any questions you'd like me to cover in the comments.